Polymers are chemicals made up of repeating units hooked together in long chains. Some polymers are commonly found in nature. These natural polymers occur all around us. In this section, we'll see why polymers have some very unique properties. First, we'll define what polymers are and look at examples of polymers that exist in nature and that we synthesize. Then we'll look at the life cycle of polymers, seeing the raw materials, how we synthesize polymers, the properties that make polymers useful to us, and then the problem of waste disposal. Polymers are an example of macromolecules, molecules that are very large, having molecular weights over 10,000 grams per mole, which is a lot larger than any molecule we've worked with so far in this class. Polymer means many units, and to build a polymer, we start with a monomer. A monomer means one unit, and like the toy model here, the monomer has two ends that can react. We bring two monomers together, and they react to form a covalent bond linking them, and that would form a dimer, or two units. We can continue to add monomers. If we add another monomer to our dimer, then we now have a trimer. And here we added another monomer to the trimer to make a tetramer. And notice that the fourth monomer added at the front of the growing chain. Since the monomers have reactive ends, two reactive ends, then chemical reaction can take place at both sides, growing into a chain. This process continues until we have a polymer, where we have 50 or more units. And here, with our toy model, we can see all of these different units linked together, and they can either coil up, or if they don't coil up, they could form a long string. Natural polymers include polymers of life, such as cellulose and starch, which are both polymers of sugars, one of which we can digest the starch, and the cellulose, or the plant material, we can't digest. Termites and cows can do that. Proteins, all of our cells are made up of, are polyamino acids. So a repeat unit is an amino acid, and here we have a generic amino acid with an R, meaning some type of chemical carbon part, R1 and R2. It's about 20 different amino acids, but they have the same formula in terms of having the same kind of two reactive ends, the NH2 on one side and the CO2H on the other side. These react together to begin to form a chain. So here we have two amino acids making a dimer. Latex is natural rubber, and that has a repeating unit, which is shown, the chemical structure is shown here. We just indicate the monomer structure and then put a bracket around it with sub N, meaning this monomer structure repeats many times, N times, to form the chain of the polymer. DNA and RNA are polynucleic acids. These are the information containing centers of our cells. Here we see that natural rubber was used by Indians of South America, retrieved from tree sap, and it was brought back to Europe and named for its ability to rub out pencil marks, the rubber. Its use and production were described in 1751. In 1802, John Gauge observed that rubber gives off heat when it's stretched. This is the observation we used in that earlier lab when we examined the energy changes of a rubber band. He also noted that rubber becomes hard and brittle when it's cold. The fact that it's hot and sticky and it's sticky in hot weather, and brittle and cold made it of limited usefulness. In 1839, however, Charles Goodyear found if he heated carbon with rubber, it underwent a change called vulcanization. It allowed rubber to preserve its properties over a much larger range of temperatures. And so eventually we could develop rubber tires for automobiles. There are many, so now we see that there are many natural polymers existing around us. With the advent of modern chemistry, we've been able to develop synthetic polymers whose properties are tuned to many different uses that we want. One of the first developments was synthetic rubber. This we saw before that natural rubber could be processed to make automobile tires, and during World War II there wasn't enough supply, especially for the Allies, of natural rubber. So there's a big push in the chemical industry to develop synthetic rubber to supply the Allied military with tires. Polyethylene is an example of another synthetic polymer, and this finds examples in bags. We'll look more closely at polyethylene in a little bit. You've all seen the sports spandex clothing. This is an example of a synthetic polymer with special stretch properties. Nylon is another synthetic polymer that was developed to replace silk stockings to make it more same look and feel, more affordable. And here's an example of how nylon is made. Nylon 6,6 is common nylon used in clothing, where once again we have two monomers that react together, and each monomer has two reactive ends. One has two NH2s and one has two COCl groups. These react together to form the growing chain of the nylon polymer. There are other examples of polymers: polyvinyl chloride, polystyrene, and Teflon. We'll look more closely at those. Well, the polymers exist around us, both natural and synthetic. And we see that they perform many useful functions for us. We usually think about the plastics according to the way we use them, but that is nearsighted. Any product has a life cycle that begins at the raw materials that come from the earth and the atmosphere. These raw materials are converted by chemical synthesis and processing into products which are further tailored for a desired set of properties. These engineered materials are then manufactured into the finished product. We use the product, and then what happens? We throw it away as waste, or we can recycle or reuse the product. Recycling completes the cycle and conserves our limited raw materials. Let's look at each one of these studies. The raw materials for polymers are synthetic polymers are petroleum. In our discussion of energy, we noted how petroleum can be refined and made into gasoline and other fuels. The largest single use for petroleum is gasoline, 47%. Most of the rest is used for other types of fuel. Only about 3% of this non-renewable resource is used as a feedstock for the chemical industry, and it's used by chemists to make polymers that we're talking about, drugs, pesticides, and other chemicals we need. There is some concern that petroleum is too valuable to burn for fuel, and we should be looking for alternative energy sources, like we talked about in the previous chapter. Chemists describe the reactions used to make polymers as either condensation reactions or addition reactions. Addition reactions involve the reactants joining together to give the polymer with no other products. The synthesis of ethylene is an example of addition polymerization, where we have a molecule of ethylene with a carbon-carbon double bond, This joins another molecule of ethylene to form a chain of carbon-carbon single bonds, and there's no byproduct. The condensation polymerization gives the polymer in a small molecule as a byproduct. For example, the synthesis of nylon results in the loss of HCl. As we saw before, the monomers for nylon in the chain, I didn't note before that for every time you make that bond, you have the byproduct of HCl to balance the chemical equation. To give you an idea of how addition polymerization works, let's look at the synthesis of polyethylene. One process uses species with one unpaired electron. We've encountered that before, free radicals. Some chemicals, like peroxides, break their covalent bonds in half to produce free radicals. These radicals then react with ethylene monomer to form a new carbon radical. This radical can react with another ethylene unit, and the process continues in this way for thousands of cycles. This is the propagation part of the cycle. Finally, the cycle ends in the termination, in which two radicals combine to form a stable compound. So we've seen what a polymer is. We can classify, and how to make polymers. We can classify polymers by their properties. Plastics are polymers that are pliable. Plastics are easily shaped and molded when they're hot, a property described as thermoplastic. Other polymers are thermoset. They don't soften or melt when heated. Finally, materials like rubber are classified as elastomers. When stretched and released, they snap back to their original shape. Plastics, the stretch of plastic, it is pliable, but it will not return back to its shape. What makes polymers different from other materials? The most noticeable difference is that polymers are large molecules. They're larger than any molecule we've discussed so far, unlike water or sugar. The long chains can be in various 3D arrangements, which give rise to the properties that are unique to polymers. Some chains are long and straight and packed together like spaghetti, dried spaghetti in a box. Others are coiled and randomly arranged like cooked spaghetti on a plate. And some polymers have branch chains like a tree rather than straight chains. The important message here is that the shapes of polymers determine their properties. Polymers may be linear or branched. Polymer chains can also join together and cross-link. These cross-link polymers are rigid and are used in resins such as Formica countertops. A new type of macromolecule is called a branched macromolecule, or a dendrimer, that has regular branching. These materials offer unique properties that may be useful for future applications. Polymer properties is also determined by how these linear or branched structures pack together. Polymers like high-density polyethylene in milk bottles are described as crystalline. Crystalline polymers have regular arrangements of their chains. Random arrangements are described as amorphous. Low-density polyethylene has its chains randomly coiled in amorphous arrangements. Most polymers are folded, not straight. Straight polymers, there are a few straight polymers such as Kevlar, which is very strong and used for bulletproof vests. So we see that the way the polymer chains, linear, coiled, folded, crystalline, amorphous, is going to have very different applications. Another way to change the properties of the polymer is to change the chemistry of the monomer. We saw polyethylene, how that is synthesized from the ethylene monomer, C2H4, and a number of related polymers can be made by modifying ethylene. by replacing the hydrogen atom with another group. If chlorine is substituted for hydrogen, vinyl chloride is obtained, the monomer, which makes polyvinyl chloride, which is used in plastic plumbing, for example. Replacing a hydrogen with a CH3 group, or methyl group, gives propylene. Polypropylene has different properties depending on how that methyl group is arranged. Other polymers, such as polymethyl methacrylate and polystyrene, are also derived from the ethylene monomer. If we replace all 4 hydrogens with fluorine atoms and polymerize it, we get Teflon. The fluorine atoms on the outer part of the polymer molecules give it the non-stick properties that we want for frying pans and Gore-Tex fibers for gloves and jackets. All of these groups that we've added to the ethylene monomer we call side chains. And the orientation of the side chains relative to each other will affect the properties of the polymer. For example, for polypropylene, there's a methyl group hanging off the chain, and that can be in different arrangements. If they're all on the same side of the polymer in a regular orientation, we call it isotactic. If they alternate front to back, we call the polymer syndiotactic. And if it's just randomly oriented, we call that an atactic polypropylene. And those isotactic, syndiotactic, and atactic polypropylenes are going to have different properties. Some can be used for clothing, some can be used for packaging, hard bottles, or film. Another way to produce a different type of polymer is to use 2 different kinds of monomers. Not all polymers have the same repeating unit. When you have 2 different monomers polymerized together, you have a copolymer. And once again, the arrangement in the chain is going to affect the properties. So we have a copolymer in which the 2 types of monomers alternate, AB, AB. You see that in the top example here, the alternating copolymer. In block copolymers, the repeating units of one group are all close together, followed by then the other group stuck together. And we can have random orientation of the 2 different monomers in the chain. We can also make graft copolymers by joining straight chains together in a network. An example of a copolymer is PETE, or polyethylene terephthalate, which is made by the chemical joining of terephthalic acid and ethylene glycol. Notice that this is a condensation reaction because the small molecule water is a byproduct for each time the 2 monomers join together. So that is how we can synthesize polymers and how the properties of the polymers depends on the synthesis. We can also modify the properties of the polymer after the synthesis by a couple of methods. One is cross-linking. Cross-linked polymers are not going to soften when heated. For example, epoxy glues and resins are cross-linked polymers. Polyimides, used for microwave cookware and cases for appliances, have high thermal stability and chemical resistance. And polycarbonates, another cross-linked polymer, also has strong properties. It's shatterproof windows and lightweight glasses. Another way to modify the properties of a polymer after you synthesize it is to add components. Plasticizers are added, which make plastics softer and more pliable. These compounds are small molecules that are volatile and can be extracted from plastics. The new car smell is due to plasticizers in seat covers and fabrics as they volatilize. Old cars have an oily film on the window due to vaporization of the plasticizers by the sun. And once the plasticizers evaporate out of the polymer, it's not as soft and therefore is more brittle, so old cars seek to crack. Recently there was a concern about plasticizers used in teethers and other baby products. Some groups were concerned about the health effects of infants ingesting these plasticizers. So now we've talked about the synthesis and the properties, and the final thing we want to talk about is the waste, the final step in the life cycle of a polymer. Let's look at the composition of our trash that we throw away. Paper and paper products are by far the largest contributor in terms of volume, amounting to about 1/3 of our trash. Plastics make up another large portion, about 11–12%. How can we reduce the volume of our waste? One way is to recycle those materials, such as paper and plastic. And here we see some of the common polymers that we have around us we use every day with the recycling codes. For PET, code 1, it's called polyethylene terephthalate, and it's used for 2-liter soda bottles. Code 2 is high-density polyethylene, which is a crystalline polyethylene, and is rigid and used for milk bottles. Polyvinyl chloride is used in clear food wraps, saran wrap, shower curtains, and is code 3. Low-density polyethylene, the amorphous form, is used for sandwich bags and grocery bags, and is code 4. Recycling code 5 is polypropylene, which is a more rigid polymer and used for plastic pill bottles. And polystyrene, code 6, is used in the hard, clear plastic cups for cold drinks, and when it's processed in a certain way to inject gas into it, makes a foam used for insulation and hot cup beverages. How do we dispose of the waste? If we don't recycle it, then we have a few choices here. Most of our trash is buried in landfills, where volume is a concern. We can reduce volume by burning the materials, but then we have the concern about air pollution. In principle, the energy from burning the trash could be used to produce electricity, replacing some of the combustion of coal or oil, but this is not realized commercially. Some plastics and other materials are designed to degrade in the environment. Bacteria and other life forms can digest them. Copolymers, for example, copolymers of starch and normal polymeric materials break down into small pieces. Plastics typically don't biodegrade, and so if we don't want to landfill them, one option is to recycle them using those codes and designations we talked about. And now you can buy furniture, shirts, decking material that's made from recycled plastics. And another alternative to generating waste is to try to reduce the amount of material we use. We really need all the paper or plastic packaging that is used in most of the goods we buy. And in our lab, we'll look at how we can separate plastics, polymers, and think about the process needed to do actual recycling for those plastics. Thank you for your time.